Okay, g'day all and welcome to another video. This video here is a little celebration video for me. I want to thank everybody for subscribing and commenting and watching the videos and just keeping me entertained. I reckon you people are a bunch of legends. Anyway, let's move on. Okay, so I want to talk about the language that I'm making. This is a new artificial intelligence language for natural language processing. It's called Isaac 0.7 and it's going to come out soon. In the coming weeks, we'll say. For more info, check out the website and the Facebook. Alright, good on yous. Okay, but on to the topic for today. So today, what I thought I might do is make a top 10 data structures that everybody should know. Well, every programmer, probably not everybody. I mean, the gardener or whatever mightn't really care about this, or the people that clean pools. But, you know, it wouldn't hurt either. But I love reading those top 10s on YouTube or watching the Mojo top 10 videos and your list 25. I don't know how accurate they are or informative, but I'm going to try and make this top 10 data structures every programmer should know pretty informative. Yeah, so if you're brand new to programming, these are the 10 data structures that I reckon you should learn. Yeah, and if you're not new to programming, if you've been programming for quite a while, you've probably come across all of these at one point or another. But hopefully this, you know, might be a bit of a refresher, or yeah, you might just like to watch it for entertainment purposes to see how I rank things. We're going to look at the most important and useful computer data structures. They're really interesting, they're really powerful, and they're also the result of many people's very, very clever people's work. And this list is just my opinion, you know, there's no real order to how good or useful data structures are, but, you know, just a bit of fun. Okay, number 10, the queue. Alright, so queues are a classic first in, first out data structure, or FIFO they call them. And they're really common, for instance, in event-driven operating systems. So the operating system is, you know, it's obviously got to figure out what order you type things at a keyboard, for instance. Otherwise, you know, the document that you're typing into wouldn't have the letters in the right order, which might be fun for a while, but eventually you're going to have to send in your assignment or whatever you're working on, and you're going to want some order to the letters that you're typing. Okay, so you hit a key on the keyboard, right? You hit a T or a H or whatever. The operating system might actually be busy when you hit that key, so it can't immediately address the fact that you've hit that key and put it in your text document. So what it'll do is it'll put that key press into an event queue. And when it gets time, when it's not copying a file or whatever the operating system does, it'll address all of the events in the event queue. But the important thing is that it's got to address them in the same order that they occurred. You know, if you type THE, it can't address the E first and then the H and then the T. It's got to, you know, it's got to remember the order that you typed them in. So for that purpose, they'll use a queue more often than not in the background. And this is how a queue works. So here I've got a bit of a queue, and all you do is you put numbers into your queue. So yeah, in this particular example, I would have put in the 5, then the 8, then the 1, then the 8 down here. And the real point to a queue is that when you take items out, they come out in exactly that same order. So we'll get out the 5 first, then the 8, then the 1, then the final 8. Yeah, that's pretty much a queue. Okay, number 9, the linked list. This is a really interesting data structure as well because it can do things that arrays can't do very well. For instance, deleting an item or inserting another item into the list. Arrays aren't so good at that. But linked lists are fantastic at that. So they allow really fast insertion and deletion of items. And the other really cool thing that linked lists can do is vary their size while the program runs. So the size of a linked list doesn't have to be any compile time constant or whatever like a C++ array does. Linked lists can grow or shrink as the program runs. They're pretty much just a series of nodes, and every node has an information or some element to it. It could be an integer or some data structure, but they also have a pointer to the next node in the list. So over here I've drawn an example of a linked list. I've got two dummy nodes, this yellow head node down here and the final node, which is a Z that points to itself. That's just a convention. You can, you know, make linked lists without those, but the actual list here is these items here, 5, 6, 1, 8, and 7. So you just follow the arrows. But the cool thing about a linked list is just how easy it is to delete and add items. So for instance, if we wanted to delete this 6 right here, all we would have to do is for the 5, we would point the 5 to whatever the 6 is pointing to. So the 5 would point to the 1, and then we delete the 6. Yeah, and it's gone. And if we wanted to add, say, a 2 up here between the 5 and the 6, well, that's pretty easy as well. All we would do is point the 2 to whatever the 5 is pointing to. So the 2 would point to the 6 down here, and then we would shift the 5's pointer to point to the 2. So our list would then be 5, 2, 6, 1, 8, 7. It's really, really fast to insert and delete items from a linked list. Number 9, the linked list. Number 8, the stack. Okay, so stacks are the classic last in, first out, or LIFO data structure. And they're used in just about every computer program in the whole world. There's really no there's no such thing as computer programs without these things, these stacks. They're used to maintain return addresses for sub-function calls. A stack is actually so useful or so fundamental to computing that CPUs themselves actually know what stacks are. The CPU's silicon itself is designed to work with a stack, a call stack, to be a bit more specific. Okay, so they're last in, first out. This is a little example over here. They're kind of the opposite to a queue. Yeah, they're brothers or sisters with the queue, but they return items in the opposite order. So if you imagine that this is just a stack of plates right here, or a stack of papers, the first paper that we push onto the stack is 8. I should say first of all that there's 2 operations you can do with a stack. You can push an item onto the stack, which means to add an item to the stack, or you can pop an item off the stack. That's the only 2 things you can do. So we push on the 8, we push on the 1, we push on the 8, we push on the 5, we push on the 3, and once we've pushed on a bunch of items onto the stack, the important thing is when we pop items off, the stack's going to give them back to us in the exact opposite order. Yeah, so the stack will pop off the items in the order 3, 5, 8, 1, 8. The exact opposite to that which we pushed them on. Number 8, the stack. Good stuff. Number 7, the priority queue. Okay, I don't like my diagram of this at all, but I really like the data structure. Alright, so have you ever needed something like a queue, but that gives you back the items in perfect sorted order, from largest to smallest, or smallest to largest? What you want in those circumstances is called a priority queue. And they're just like queues or stacks, except instead of giving you like the top item on the stack or the first item in the queue, a priority queue will give you the item with the highest priority. So it's up to the programmer or the implementation what that priority is, but it might actually be the magnitude of a number, for instance. Like over the side here, what I've got. So this is just a picture of a priority queue. If we can imagine that we put items into our priority queue in a random order. Maybe we put them in exactly this order. So we put in the 4, then the 15, then the 71, then the 64, then we put in the 13. But then when we take the items out, the priority queue is going to give them to us in exactly sorted order. So it's going to give us a 71, then it's going to give us a 64, then the 15, then the 13, and then the 4. No kidding, that's how priority queues go. They're pretty good stuff, really. Interesting data structure. What's even more interesting is just how in the world would you implement that? If I ever get a chance, I'd love to do some videos on some clever implementations of these things. Because seriously, the people that have studied this stuff in the past, like the legacy of computer science, it's absolutely magical stuff. And I'd love to go through a bit of that and implement a priority queue or 2. Alright, what do we got down here? Priority queues are indispensable in many algorithms which use heuristics, such as pathfinding. Yeah, they are too. So the A-star pathfinding is what I was thinking about particularly there. What the A-star pathfinding algorithm does is it looks at all of the paths from its present position, and it judges them as to, how good they seem to how good they seem to be to the exits, or how close they seem to be to the exit of the maze that you're trying to solve. But the thing about it is it makes a big list of possible paths that it could take, And the A-star algorithm always tries to pick the most likely path to lead to the exit the quickest. And it does that with a priority queue. Or I should say that a priority queue can help it do that very, very fast. Otherwise, the A-star algorithm, you might just be looking through a list of possible nodes every time, some unsorted array, and it's just going to take a really long time. But a priority queue makes the A-star algorithm really fast. Okay, number 7, the priority queue. Number 6, the hash table. Okay, so this is a really good data structure as well, extremely powerful. So hash tables are really closely linked to another general concept, which is just called hashing, which is a really interesting read as well. But it's often used to solve what's called the dictionary problem, and it's pretty much just an array, but it's not necessarily indexed by integers. You index items in a hash table by these things called hash keys. And the cool thing about hash keys is that they can be anything. They don't have to be integers. They could be floats or even complex data structures themselves. Anything that can generate a hash could be used as a hash key. And you can pretty much write your own hash functions for any data type whatsoever, and make a hash table with really quick lookups with any arbitrary data type. Super interesting topic. But if you imagine, over here I've just got a very, very simple hash table, and the hash keys are letters of the alphabet. Yeah, so the hash keys in a really simple circumstance might just be the first letter of a bunch of strings. It's not often the case, but you might do this. So that's my diagram over here. Usually your hash key wouldn't just be the first letter of a string. If you imagine that you've got a list of millions of names or billions of names, and you're trying to search it thousands and thousands of times a second for particular names. So you've got a list of 1 million names and you want to know if the name Tim is in there. If your list is unsorted and you've got to search through the entire list to see if the string Tim is anywhere in the list, millions of names, it's going to take a long time to do that search. And then if you've got to do a few searches a second or thousands of searches a second, you've got no chance with an unsorted list. You've got no chance. Buckley's chance, we say. But with a hash table, we can do exactly that. So all that we really do with a hash table is we sort of set up a dictionary-like structure. So instead of searching through all of the names in your list, you would turn straight to the page T, right down here, and you would check if Tim is there. Well, Timothy is, so I guess we'll count that. Yeah, so that's kind of how a hash table works. There's a lot of questions to be answered when you're actually implementing a hash table, but I hope you get the general idea that a hash table is pretty much used for really fast indexing of arrays without necessarily using integer indexes. Yeah, that's pretty much what they're all about. Number 6, the hash table. Okay, number 5, the binary tree. Here we go. So binary trees are really, really versatile, and the concept is super, super simple. There's just a collection of nodes, and each node has 2 child nodes, and each node has 1 parent. Except for this top node up here, which, it might have a dummy node in your implementation. It's up to you. But at the moment, it doesn't have a parent. Yeah, and these bottom nodes down here don't have children either. Or their children are null, you might say. How sad for them. But the amazing thing about the binary tree is just how useful this simple idea is. So it's used for so many different things. There's binary search trees, we got heaps. There's other searching algorithms and sorting algorithms. Binary trees are all over the place in computer science, and so are other trees. Like there's other trees as well. There's ternary trees, or I don't know what you'd call a tree with 4 child nodes, but yeah, just pretty much tree structures are absolutely everywhere in computer science, and especially binary trees. Binary trees are often used to transform an algorithm from what would be big O linear time to big O log n time. And that is a huge, huge gain. Yeah, that's a massive gain. From linear time to log n. It's a very, very good gain. So the binary tree, number 5 in my excellent list. Okay, number 4, the vector. Alright, so this one's a little bit debatable. I didn't really know what the best term to use would be, but I decided to call it a vector. But I want you to know I'm not talking about STL vectors here, and I'm not talking about Euclidean vectors either with direction and magnitude. All I mean is little arrays of numbers. So your float 3 or the SSE registers, those kinds of things. They're just little arrays, obviously, but these particularly small arrays have a really special place in computing. To the point where a modern CPU and a modern GPU, like the hardware itself, is pretty much built to number crunch with these vectors. SIMD programming in recent years has really taken off, and SIMD programming is nothing but vectors. Nothing but vectors. Okay, so what can vectors do? Well, they can store a position. Here I've got a 3D position, player.pos. I got a pixel just here, RGB, red, green, blue. Yep, vectors can store pixels pretty easy. They can also store normals, so your surface normals or corner normals or, line or face normals, anything you like. They can store all sorts of different information, from 3D positions to different colors. And yeah, like I said before, most of modern hardware, or a lot anyway, of the efforts in designing modern hardware is primarily concerned with how to do vector operations as quickly as possible. We've got some amazing hardware nowadays, and yeah, part of the reason it's so amazing is the incredible instruction sets that modern hardware has to do with dealing with vectors, I should say. Okay, number 4, the vector. Number 3, here we go. We're really getting to the crux here. The matrix, the marvelous matrix. What a fantastic idea. A matrix is usually a multi-dimensional array with a collection of predefined operations. So matrices aren't physically different to just arrays. A 2D matrix is really just a 2D array in RAM. But conceptually they're different, so we tend to do different operations with matrices. For example, we've got the matrix product, which is, you could do it on a 2D array, but to me that would make the array a matrix. I hope that makes sense. There's not a great deal of difference between a matrix and an array anyway. For most of their history, matrices were actually known as arrays, according to Wikipedia anyway. So matrices have become ubiquitous in graphics programming because they've got this really, really weird ability and just extraordinarily powerful ability that more than one transformation can be stored in a single transformation matrix. So you could store a rotation, a scale, a translation, all in the same matrix, and then multiply all of the vectors in your 3D scene by that matrix. And hey presto, all of the vectors would have all 3 of those transformations applied to them. It's really, really fast. It's really fast. And it's yeah, really quite magic. There's no other way to explain what matrices do. It's absolute magic. But here I've got a few. I don't know why I chose to draw these ones out, but we've got what's this? A 2D scale. Yeah, if you want to do a 2-dimensional scale, you might use a scaling matrix. Yeah, this is just a standard matrix product here with a vector, so x and y would be a vector, and that's the matrix multiplication right there that would scale that vector. We've also got a 2D rotation with a matrix. Yeah, you just whip out a bit of Pythagoras or whoever invented all of that triangle stuff. I can't remember his name, but cos, sine, trigonometry. Trigonometry they call it. Yeah, it's not someone's name. Yeah, you whip out a bit of trigonometry in a matrix and you've got yourself a 2D rotation, so it's extraordinarily powerful. But the other cool thing that you could do, and what I was trying to talk about over here in this middle paragraph, is if you multiply this 2D rotation matrix by this 2D scale matrix, then you'll get a single matrix that you can multiply by your vector that does both the scale and the rotation. It's very, very cool. And down here I've got a 3D identity matrix for for no reason at all. So the identity matrix doesn't do anything. If you multiply a 3D vector by that, you'll just get your 3D vector back. So that's not very productive. Also interesting is the topic of adjacency matrices. Yeah, I tell you what. Matrices are absolutely amazing. I can remember being in maths class, and my lecturer was telling the class about adjacency matrices, and he was squaring them and cubing them and multiplying them together, and he was saying what you can do with adjacency matrices, and I was just thinking to myself, you can do what with matrices? It sounds like he wasn't doing anything rude with them, I don't think. That I could see. I couldn't see him doing anything rude with the matrix. But just what he was describing, it's incomprehensibly powerful. It's so incredibly useful and so simple. So you can really answer utterly mind-boggling questions with a couple of matrix multiplications. It's really interesting topic. So if you ever have the time, if you've not looked into it, go and have a good read of adjacency matrices and see exactly what happens when you square an adjacency matrix a few times. You get some pretty interesting information. Okay, well, the amazing matrix is number 3 on my list. And number 2, the array. Okay, so things don't get much more fundamental than this, the mighty array. I tell you, you can't program for too long without using at least 540 million arrays. They're that common. Seriously, these things are absolutely everywhere. So an array is just a collection of variables, each with a unique numerical index. Or more to the point, they're a collection of variables that you can instantly look up elements by their integer address. So for instance, you could look up item number 6, and it'd be 144 over here in my array. Or you could change the value of element number 3, which would be negative 23 over here in my array. Whatever you want. So they can look up items really quickly and change items really quickly. They can't delete and add new items so quickly, unless you're adding items to the end of it. Yeah, but they're pretty good at some things and not so good at others, so linked lists are better at that. But arrays allow really fast index-based lookups, and they form the basis of many, many other data structures. So if you're making a matrix, you'll probably use an array. If you're working with vectors, you're obviously working with arrays. A lot of the time, trees are also implemented with arrays. I mean, you can't really program very much without using at least some arrays every now and again. You know, just they're everywhere. So here's a little array over here. These boxes in yellow would be the indices. You don't actually store that in your array, but this is the array just here: 65, 12, 162, yeah, all the way up. So the array, or arrays, are one of the most fundamental of all data structures, and actually, this is pretty interesting really, but if you think about it, the computer's memory is nothing but a huge array. So whenever you address memory, you type, some 0xADFF sort of weird looking hex thing, but all you're doing there is just typing out an integer index for a huge array. So the computer's RAM is nothing but an array. Number 2 on my list, the array. And drum roll. What's number 1? The scalar variable. Here we go. Okay, so why did I put this as number 1? Why is this even a data structure? Well, I'd have to say that it's a data structure. It's more than a data structure. It's the data structure. Computers actually, if you've ever thought about it, they do nothing other than read and edit scalar variables. That's all they can do. That's all they do, read and write variables. And a single variable itself is pretty useless. It could have a 5 or a 12 or whatever, but it's fairly pointless. But to control hundreds of scalar variables, or millions of scalar variables, or billions of them, and to have them all sing together in a gigantic symphony, forming inconceivably complex interactions and building every single other data structure that we've been through, all from nothing but a bunch of ones and zeros. To control a scalar variable is one of the most fascinating adventures in thought you could possibly have. And it's fundamental to what it means to problem solve itself, or to question and to answer. I tell you, controlling scalar variables is deeply rewarding. It's also very punishing at times. Sometimes they don't behave themselves. But controlling scalar variables is what programming is all about. It is computer programming. So I've put number 1 on my list, the atoms of the digital world themselves, the scalar variables. And here I've drawn a few. Why not? So we got a signed int set to negative 52. I got an unsigned int, which I decided to write out in hex for no reason at all. I've got a float in scientific notation. I've got a bool down here, which has got 2 values in it for some reason. I've got a byte and a char. So number 1 on my list, the scalar variable, the most important data structure of them all. And that's about it. Okay, well thank you very much for watching all. I hope that was enjoyable, and I hope I get another video up shortly. Cheers all. Have a good one.